A university will begin a 13-day period during which students may register for the semester. Of 13 days, the number of elapsed days before a randomly selected student registers has a continuous distribution with density function ft that is symmetric about t is equal to 6.5 and proportional to 1 over t plus 1 between days 0 and 6.5. A student registers at the 60th percentile. Calculate the number of elapsed days in the registration period for this student. So we are given that the time t could be anywhere between 0 and 13 days. T is the time before a student registers. And it's symmetric, the PDF is symmetric about t equals 6.5. So what that means is, since it goes from 0 to 13, and it's symmetric about 6.5, so it means that between 0 and 6.5, we have half of the probability. So 0.5 would be the integral from 0 to 6.5 of f of t. And we are told also that between 0 and 6.5, the PDF is proportional to 1 over t plus 1. So that means it's equal to a constant over t plus 1. And so when you integrate this, you get c ln 1 plus t from 0 to 6.5. So c ln 7.5 minus ln 1. ln 1 is 0. And now when you divide both sides by ln 7.5, see on the left side you have 0.5. So you get the constant as 0.24815. Now k is the 60th percentile. And that means that the probability t is less than or equal to k is 0.60. Now we would love to use the same expression for the PDF now that we have the constant, and we would love to say that, okay, now the accumulated probability is 0.6, so we would like to place 0.6 here, and then we would go 0 to k, f of t, and then use this f of t with the c known, and things look very simple. The problem is that this proportionality is given only from 0 to 6.5, which means it's only, this expression is only valid for the PDF in the, so this expression for PD, and between 0 and 6.5, the accumulated probability is 0.5. So what that means is that this expression is only valid as long as you're dealing with a cumulative probability of 0.5 or less. And this one is 0.6. So we can't put a 0.6 here and still use this expression. So now to get around this issue, what we do is we again use symmetry of the situation. So this is a situation. K is the 60th percentile. So K, the time K happens at cumulative probability 0.6. And the total time is 0 to 13. So if this is time K, then the remaining time is 13 minus K. And this length is 13 minus K. And by symmetry, we'll have a 13 minus K length here at probability 0.4, because this remaining probability is 0.4, and that has length 13 minus K. So the initial probability of 0.4 will also have length 13 minus K. So now that's only possible because we have symmetry here. Okay, symmetry around 6.5 means that you go some distance, and if you take the same distance in the beginning, then whatever probability you have over here, the same probability you have in the beginning. So now from here we see that probability that t is less than or equal to 13 minus k is 0.4, because it's 1 minus the probability t is less than or equal to k, so 1 minus 0.6, so that's 0.4. And now this 0.4 is less than 0.5, so therefore now we can use the expression that we have for the PDF in the first half, which is C over 1 plus T, and C has been found to be 0.24815. And so 0.4 is equal to probability T is less than or equal to 13 minus K, which means 0 to 13 minus K integral of the PDF. And again, this integrates to ln 1 plus T. So ln 1 plus 13 minus K minus ln of 1 when you put T equal to 0. And that was equal to 0.4. And so we can now divide by 0.24815. ln 1 is 0 as before, and this becomes 14 minus K. So when you divide both sides by 0.24815, you get 1.612. Then you raise both sides to the power of E. So 14 minus K is equal to E power 1.612. And you evaluate the E power 1.612, move the K here, subtract this one from 14, and you get K equals 8.99. That's choice C.